Out there in the endless black, beyond the faint glow of stars we can see, lies a universe that refuses to give up its secrets. Think about that for a moment. We've sent probes to the edge of our solar system, built telescopes that peer back in time, even stood on the surface of another world. And yet, space still holds mysteries so profound, they make even the brightest scientists pause. What if I told you there are questions about the cosmos, big, fundamental, mind-bending questions that no one, not even the experts, can fully answer? That's the humbling truth. The more we learn, the more the universe seems to whisper, "You haven't figured me out yet." Picture this: a black hole so massive it defies logic, galaxies that spin in ways physics says they shouldn't, signals from deep space that repeat without explanation. These aren't plot twists from a sci-fi movie, they're real, unsolved puzzles written in the fabric of reality itself. And they're just the beginning. From the eerie silence where alien civilizations should be, to the invisible force ripping the universe apart faster than we can measure, the cosmos is full of riddles that keep astronomers up at night. But here's the thing, these aren't just problems for scientists in lab coats. They're invitations to wonder, to imagine, to stand at the edge of what we know and stare into the unknown. That's exactly what we're doing today. We're diving headfirst into 30 of space's most baffling questions, the kind that challenge everything we think we understand. Some might shake your perception of reality, others will leave you with more questions than answers. But that's the beauty of it, because the universe isn't just a place we explore. It's a story we're part of, one where every mystery pulls us deeper into the grandest adventure there is. So if you've ever looked up at the night sky and felt that tug of curiosity, you're in the right place. Buckle up. By the time we're done, you'll see the stars and the gaps between them in a whole new light. What if we told you that every galaxy, star, and atom in the cosmos sprang into existence from a single, unimaginably dense point? The Big Bang is the story we tell about the birth of the universe, but here's the catch: it doesn't explain what came before. And that's where things get truly strange. Think of it like this: if the Big Bang was the ultimate starting gun, what was in the room before the race began? Some theories suggest our universe might be just one bubble in an endless froth of multiverses, each with its own laws of physics. Others propose that time itself didn't exist before the Big Bang, making the question meaningless, like asking what's north of the North Pole. Then there's the quantum realm, where particles blink in and out of existence seemingly from nowhere. Could the universe have emerged from a random fluctuation in this cosmic static? But the real challenge, defining nothingness. Empty space isn't truly empty, it's seething with energy. So was there ever really nothing? Or is the idea of true nothingness just a human concept that doesn't apply to the cosmos? This question doesn't just test our theories, it exposes the limits of human imagination. After all, how do you picture a state where time, space, and even the laws of physics didn't yet exist? That's why scientists grapple with this puzzle. It's not just about filling in a blank spot in history, it's about rewriting our understanding of reality itself. Every attempt to answer this question bends the rules of physics to their breaking point, revealing just how much we still don't know. And that's what makes it one of the most thrilling mysteries in all of science. We've all looked up at the night sky and wondered, does it ever end? The idea of an infinite universe stretches our minds to the breaking point. Yet scientists have been wrestling with this very question for centuries, and the answers they've found only deepen the mystery. Take the cosmic microwave background, the faint afterglow of the Big Bang. Its patterns suggest a universe that's flat, meaning parallel lines would never meet, a strong hint that space might go on forever. But here's the catch: if the universe is truly infinite, why does it look so similar in every direction? Shouldn't there be endless variations, repeating structures, or even other versions of you in some distant corner? This is the paradox that keeps cosmologists awake at night. Then there's the curvature of space itself. Some theories propose that the universe might be like the surface of a vast, four-dimensional balloon, finite, but with no edges. If you traveled far enough in one direction, you might end up right back where you started, like an astronaut circumnavigating a cosmic globe. Yet every time we measure, the universe seems stubbornly flat with no detectable curvature. So which is it? An endless ocean of galaxies or a colossal loop we just can't see? And let's not forget the philosophical weight of infinity. If space truly has no end, then somewhere out there, every possible configuration of matter must exist. Other Earths, other civilizations, even other versions of history playing out in the dark. It's a dizzying thought, one that forces us to confront whether we're just a speck in an unfathomable vastness or part of something even stranger. That's the real challenge here. The universe doesn't just defy our measurements, it defies our very capacity to imagine it. Every answer we find seems to open up new questions, leaving us humbled by the sheer scale of what we don't know. Imagine something invisible making up 85% of the matter in the universe, a ghostly substance that refuses to shine, reflect, or absorb light, yet bends galaxies with its gravitational grip. That's dark matter, the universe's most frustrating disappearing act. We know it's there because galaxies rotate too fast for the visible stars alone to hold them together, like a carousel spinning so wildly its riders should fly off, yet somehow they don't. The missing glue, dark matter, but here's the kicker: after decades of searching, we still don't know what it actually is. Scientists have chased shadows in the dark with detectors buried deep underground, shielded from cosmic noise. The leading suspects: WIMP, weakly interacting massive particles, hypothetical heavyweights that barely touch ordinary matter, passing through you right now like phantoms. But after exhaustive hunts in mines and labs, WIMP remain elusive, leaving researchers to wonder if they're chasing the wrong ghost. Then there are actions, ultralight particles so wispy they could dance through lead like it's empty space. Theorists love them, but catching one is like trying to trap a whisper in a hurricane. Even stranger are the experiments that came up empty. Giant vats of liquid xenon waiting for a single atomic recoil, a ping from the dark. Yet year after year, the detectors stay silent. It's as if dark matter is taunting us, leaving gravitational breadcrumbs but dodging every net we throw. Some physicists are now questioning the rules of the hunt entirely. Could dark matter interact with forces we haven't discovered yet? Or worse, what if it's not particles at all, but a flaw in our understanding of gravity itself? This isn't just academic frustration. Crack this mystery and you rewrite the story of how galaxies form, how the cosmos evolved, even what holds reality together. Every empty detector, every unexplained galactic twist is a clue or a cosmic red herring. One thing's certain: dark matter isn't just hiding, it's teaching us how much we still don't see. Every atom in your body, every star in the sky, even the air you breathe, all of it exists because of a cosmic fluke that physicists still don't fully understand. According to the laws of physics, the Big Bang should have created equal amounts of matter and antimatter, particles that are identical but with opposite charges. When matter and antimatter meet, they annihilate in a flash of energy. So why didn't the universe self-destruct instantly? Somehow, for every billion antimatter particles, there were 1,000,000,001 matter particles, and that tiny surplus is the reason anything exists at all. This imbalance, called Baryon asymmetry, is one of the most baffling gaps in our understanding of reality. Scientists first glimpsed a possible clue in the 1960s when they observed something called CP violation, a subtle quirk where particles and their antimatter counterparts don't behave quite symmetrically. Imagine flipping a coin and finding it lands on heads 51% of the time instead of 50. That slight preference, magnified across the entire cosmos, might explain why matter won out. But here's the catch: the CP violations we've measured so far are far too small to account for the overwhelming dominance of matter today. That's where wilder theories come in, like leptogenesis, the idea that ultra-heavy neutrinos in the early universe decayed unevenly, producing more matter than antimatter. These ghostly particles barely interact with anything, yet they might hold the key to our existence. Or perhaps the answer lies in cosmic phase transitions, moments when the infant universe shifted states like water freezing into ice, creating defects that tip the scales. Some scientists even speculate that antimatter-dominated regions might exist somewhere in the void, separated from us by unimaginable distances. The stakes couldn't be higher. Without this imbalance, stars, planets, and life itself would never have had a chance to form. So every time you take a breath or feel sunlight on your skin, you're experiencing the aftermath of a battle fought in the universe's first microseconds, a battle we're still struggling to explain. And that's what makes this mystery so thrilling. It's not just about particles and equations, it's about why we're here at all. At the heart of every black hole lies a riddle that defies the laws of physics as we know them, a point of infinite density called the singularity. According to Einstein's general relativity, gravity here becomes so intense that space and time cease to behave normally, crumpling into an infinitely small, infinitely dense knot. But infinity isn't just a mathematical quirk. It's a flashing red warning sign that our understanding of reality is incomplete. Because in nature, infinities don't exist, they're placeholders for. We don't have the right tools to describe this yet. Enter quantum mechanics. While relativity paints the singularity as an inescapable endpoint, quantum theory suggests particles can't just vanish into oblivion, they have to go somewhere. This clash has spawned wild alternatives like Planck stars. Imagine a black hole's core not as a pit of nothingness, but as a tiny, ultra-dense remnant, a nugget of matter squeezed to the smallest possible size by quantum forces before recoiling like a compressed spring. Some theories even suggest this rebound could explain mysterious cosmic flashes or the birth of new universes. Then there's the wormhole scenario, the idea that singularities might be tunnels to other points in spacetime. Picture folding a piece of paper so two dots touch. A black hole could be the puncture connecting them. But here's the catch: traversable wormholes would require exotic matter with negative energy, something we've never observed. And even if they exist, the tidal forces near a singularity would shred anything trying to pass through into atoms. The real tension here isn't just about black holes, it's a battle between two titanic theories. Relativity governs the cosmos on grand scales, while quantum rules the subatomic world. Yet in the heart of a black hole, where gravity and quantum effects collide, both frameworks crumble. Solving this paradox might require rewriting physics itself, revealing a deeper layer of reality we've yet to glimpse. Until then, the singularity remains the ultimate cosmic vault, locking away secrets we're only beginning to dream of uncovering. We gaze up at a sky teeming with hundreds of billions of galaxies, each home to trillions of stars, and yet the cosmos echoes with silence. This contradiction lies at the heart of one of science's most haunting questions. If the universe is so unimaginably vast, why haven't we found any trace of other civilizations? Italian physicist Enrico Fermi captured this dilemma in a single, devastating query. Where is everybody? The math seems undeniable. Take the Drake equation, a formula estimating the number of detectable alien societies. Plug in conservative numbers, planets per star, the fraction suitable for life, and the results suggest thousands, even millions of civilizations should exist in our galaxy alone. But after decades of scanning the skies with radio telescopes and analyzing exoplanet atmospheres for biosignatures, we've found nothing. That eerie absence is the Fermi Paradox, a riddle that grows stranger with every new discovery. Consider the exoplanet revolution. We've now spotted over 5,000 worlds orbiting distant stars, many in the Goldilocks zone where liquid water could exist. Some, like Kepler 452b, are eerily Earth-like. If habitable real estate is so common, why does life seem to be a solo act? One grim answer is the rare Earth hypothesis, the idea that while planets abound, the precise cocktail of factors needed for complex life, a stable moon, plate tectonics, a protective magnetic field, might be extraordinarily unlikely. Earth could be a cosmic fluke, a statistical outlier in a universe mostly filled with microbial existence or barren rocks. But there's a flip side. Maybe intelligence isn't the inevitable endpoint evolution prefers. Dinosaurs ruled for over 160 million years without inventing radio telescopes. Or perhaps advanced civilizations self-destruct quickly, snuffed out by climate disasters or AI before they can colonize the stars. Some theorists propose darker solutions. Predatory alien societies might enforce radio silence to avoid detection, turning the cosmos into a galactic game of hide and seek. Then there's the possibility we're looking for the wrong signs. SETI traditionally scans for radio waves, but advanced aliens might communicate with neutrino beams or quantum entanglement technologies we can't yet detect. Or they could be so alien, their very concept of communication is incomprehensible to us. The truth might be hiding in plain sight, masked by our own assumptions. This isn't just academic speculation. The answer reshapes humanity's place in the cosmos. Are we a miracle, a mundane accident, or something in between? With every silent exoplanet and empty radio band, the universe seems to whisper two equally terrifying possibilities. We're either profoundly special or utterly insignificant. And that's what makes this paradox so gripping. It's not just about aliens, it's about whether the night sky is a promise or a mirror reflecting our solitude back at us. The universe isn't just expanding, it's accelerating, racing outward faster with every passing moment. And the mysterious force behind this runaway cosmic speed up. We call it dark energy, but that's just a placeholder for our ignorance. Picture blowing up a balloon with dots on its surface. As the balloon inflates, the dots move apart. That's the standard expansion we've known about for decades. But now imagine the balloon suddenly starts inflating faster, as if an unseen hand is pumping air into it at an ever-increasing rate. That's what dark energy is doing to the fabric of space-time itself. When astronomers first discovered this acceleration in the late 1990s by observing distant supernova, it shattered expectations. Gravity should be slowing the cosmos down, not revving it up. The leading explanation, Einstein's old fudge factor, the cosmological constant. He originally inserted this mathematical term into his equations to keep the universe static, calling it his greatest blunder when expansion was later proven. But today, it's back in vogue as a possible representation of dark energy, a property of empty space itself that exerts negative pressure, stretching the universe apart. Think of it like a cosmic spring buried in the vacuum, eternally uncoiling. But here's the twist. Calculations suggest the cosmological constant strength should be 120 orders of magnitude larger than what we observe. That's like predicting a tsunami and getting a ripple instead. This staggering discrepancy has physicists exploring wild alternatives like quintessence, a dynamic energy field that ebbs and flows over time, unlike the constant uniformity. Imagine dark energy as a cosmic mood, sometimes pushing galaxies apart aggressively, other times barely nudging them. Some models even suggest quintessence could eventually reverse, collapsing the universe in a big crunch. Then there's the radical possibility that Einstein's gravity itself needs rewriting. Modified gravity theories propose that on cosmic scales, gravity weakens differently than predicted, mimicking dark energy's effects without any exotic force. It's like realizing the rules of your car's engine were wrong all along. The weird acceleration isn't due to hidden fuel, but because you misunderstood how the pedal works. The stakes couldn't be higher. Dark energy makes up 68% of the universe's total energy budget, yet we have no idea what it truly is. Is it the energy of the vacuum, a new fundamental field, or a glaring sign that our grasp of physics is missing a crucial chapter? Every unanswered question about dark energy isn't just a gap in our knowledge, it's a crack in the foundation of reality as we know it. And that's what makes this mystery so electrifying. The universe isn't just expanding, it's running away from us, daring us to catch up. The story of life's origins might not even be an earthly tale, it could be written in the stars. Two competing theories vie for the spotlight. Panspermia, the idea that life's building blocks hitchhiked across space on comets or asteroids, and abiogenesis, the notion that life emerged from non-living chemistry right here on our planet. Both scenarios sound like science fiction, but the evidence for each is etched into the fabric of the cosmos itself. Let's start with panspermia's strongest advocates, extremophiles. These hardy microorganisms thrive in conditions that would obliterate most life. Boiling hydrothermal vents, the crushing depths of ice sheets, even the radioactive wreckage of nuclear reactors. If microbes can survive such extremes on Earth, could they endure the vacuum of space? Experiments on the International Space Station say yes. Bacteria like Deinococcus radiodurans, nicknamed Conan the Bacterium, have weathered years of cosmic radiation exposure outside the ISS, lending credence to the wild idea that life might be more of a cosmic vagabond than we thought. Then there's the chemical breadcrumb trail. Nebulae, those colossal clouds of gas and dust, are peppered with organic molecules like formaldehyde and hydrogen cyanide, the same ingredients used in labs to synthesize amino acids. In 2020, astronomers even spotted glycolaldehyde, a simple sugar, in a star-forming region 8,000 light-years away. It's as if the universe is prepping a cosmic kitchen, mixing life's recipe before planets even form. But abiogenesis has its own compelling case. The Miller-Urey experiment in 1953 showed how lightning in Earth's primordial atmosphere could spark amino acids into existence, life's Lego blocks assembling themselves. Yet critics point out flaws. Early Earth's atmosphere might not have been the methane-rich soup Miller simulated, and amino acids are a far cry from the complex machinery of a living cell. The leap from chemistry to biology remains a chasm no experiment has bridged. Perhaps the truth lies somewhere in between. Comets like 67P, studied by the Rosetta mission, contain phosphorus and glycine, key pieces of DNA and proteins. Maybe Earth's chemistry got a head start from space-delivered ingredients, then cooked up life in tidal pools or volcanic vents. Or maybe life began multiple times in multiple places with only one lineage surviving. This isn't just academic curiosity. If panspermia is real, life could be everywhere, seeded like dandelion fluff across galaxies. If abiogenesis is unique to Earth, we might truly be alone. Either way, the answer redefines our place in the universe, not just as inhabitants of a pale blue dot, but as potential citizens of a cosmos teeming with silent, ancient connections. How is it possible that the tiniest tweak to the universe's rulebook would erase life as we know it? Gravity could have been slightly stronger, electromagnetism a fraction weaker, but instead the cosmos landed on a razor-thin edge where stars burn, atoms bond, and planets form. This eerie precision is called fine-tuning, and it sparked one of the most heated debates in science. Is the universe's perfect calibration for life just lucky or something more? First, the numbers that'll make your head spin. The cosmological constant, which governs dark energy's push, is fine-tuned to 1 part in 10 to the 120. That's like firing a bullet across the observable universe and hitting a single, predetermined atom. If gravity were just 5% stronger, stars would burn out too quickly for life to evolve. If the strong nuclear force varied by even 2% carbon, the backbone of biology wouldn't form in stellar furnaces. Even the ratio of electrons to protons can't waver without collapsing cosmic chemistry altogether. The list goes on, each fundamental constant balanced like a house of cards in a hurricane. Enter the anthropic principle, the idea that we observe these perfect conditions precisely because they're the only ones that allow observers to exist. It's like a puddle marveling at how perfectly its hole fits it, but this explanation feels unsatisfying to many. Sure, we're here because the numbers work, but why do they work? That's where multiverse theories throw the doors wide open. Imagine a cosmic casino with infinite slot machines, each representing a universe with randomly dialed constants. Most combinations are duds universes that collapse instantly or never form atoms. But in a few rare jackpots, the settings align just right for life. We're simply in one of the winning universes, no designer required. Yet the multiverse isn't the only contender. Some physicists propose a deeper, undiscovered law that locks constants into their life-friendly values, a theory of everything we haven't cracked yet. Others flirt with more controversial ideas, like a universe intentionally engineered by advanced beings or higher dimensional physics we can't perceive. Here's the rub: fine-tuning forces us to confront questions that blur the line between science and philosophy. Is our existence a fluke or a feature? A cosmic accident or evidence of something grander? Every new discovery, from the Higgs boson to gravitational waves, either tightens the screws on these razor-edge constants or hints at layers of reality we've yet to uncover. And that's why this mystery cuts so deep. It's not just about how the universe works, it's about why it works for us at all. Out in the depths of space, something is firing off bursts of radio waves so powerful they outshine entire galaxies, and then vanishes without a trace in less time than it takes to blink. These are fast radio bursts, or FRB, some of the most enigmatic signals ever detected. Picture a cosmic strobe light flashing with the energy of 500 million suns, then disappearing before we can even turn our telescopes toward it. The mystery: we still don't know what's causing them. The first FRB was discovered in 2007, buried in old radio telescope data like a cryptic message waiting to be decoded. Since then, we've detected hundreds more, some repeating at random intervals, others exploding just once and never heard from again. Their unpredictability makes them maddeningly hard to study, like trying to catch a lightning strike in a bottle. But when we do catch one, the details only deepen the puzzle. Some bursts last mere milliseconds yet release more energy than our sun emits in decades. Others arrive with a telltale twist in their radio waves, suggesting they've traveled through incredibly strong magnetic fields, the prime suspect. Magnetas, super dense, highly magnetized remnants of dead stars. These cosmic powerhouses have magnetic fields so intense they could strip the data off a credit card from halfway across the solar system. In 2020, astronomers finally linked an FRB to a magneta in our own galaxy, a smoking gun that seemed to crack the case. But here's the twist: that burst was thousands of times weaker than the distant FRBs we've observed. It's like finding a firefly and using it to explain a supernova. That gap has led to wilder theories. Could FRBs come from colliding neutron stars, spraying out energy like cosmic shrapnel? Or perhaps they're the death throes of evaporating black holes, leaking radiation as they fade from existence. Some have even dared to speculate: could these be artificial signals, the equivalent of interstellar lighthouses or propulsion beams from advanced civilizations? The repetition of certain FRBs adds fuel to that fire. Why would a natural phenomenon repeat on no discernible schedule, like a radio with a stuck button? Yet for all the speculation, one thing's clear: FRBs are more than just cosmic oddities. Their radio waves carry fingerprints of the intergalactic medium they've traveled through, offering a new way to map the universe's hidden matter. And every time we detect one, it's a reminder of how much we still don't understand about the high-energy chaos unfolding in the cosmos. Whether they're magnetas misbehaving, black holes evaporating, or something we haven't even imagined yet, fast radio bursts are the universe's way of keeping us guessing. And that's exactly what makes them so thrilling. Time travel isn't just the stuff of sci-fi movies, it's a real possibility woven into the fabric of Einstein's equations. The secret lies in the way gravity warps space-time, creating pathways that might, under the right conditions, bend time itself into a loop. Take wormholes, for instance. These cosmic shortcuts, predicted by general relativity, could theoretically connect two distant points in space-time, like folding a piece of paper so the ends touch. If you could traverse one, you might emerge not just somewhere else, but someone else. But here's the catch: wormholes require exotic matter with negative energy to stay open, a substance we've never observed. Even if they exist, the slightest disturbance, a single photon out of place, could collapse the tunnel in an instant, trapping you in an eternal paradox. Then there's the Tipler cylinder, a mind-bending concept straight out of a physicist's daydream. Imagine a massive, ultra-dense cylinder spinning at near light speed. According to mathematician Frank Tipler, this rotation would twist space-time around it like a candy stripe, creating what's called a closed time-like curve. If you followed this curve, you'd end up right back where you started, not just in space, but in time. It's like running laps on a cosmic track where every loop takes you further into the past. But before you start sketching blueprints, there's a problem. The cylinder would need to be infinitely long and made of materials denser than anything known to exist. Quantum mechanics adds another layer of weirdness with retrocausality. The idea that particles can influence events in their own past. Experiments with entangled particles suggest that measurements made in the present can seemingly alter outcomes that already happened. It's as if the universe keeps rewriting its own history, blurring the line between cause and effect. Some theorists argue this could open a backdoor for sending information, or even matter, backward in time. But the moment you try to exploit this for actual time travel, you slam into paradoxes like the infamous grandfather problem. Go back and prevent your own birth, and how could you have traveled in the first place? That's where speculative physics steps in with wild workarounds. The multiverse theory suggests every time-altering act spawns a new timeline, sidestepping paradoxes by branching reality. Or perhaps the universe enforces a cosmic censorship, altering events just enough to prevent contradictions, like a safety net woven into the laws of physics. The truth is, time travel sits at the edge of our understanding, where relativity and quantum mechanics collide. Every theoretical pathway comes with its own set of impossibilities, as if the universe is teasing us with solutions just out of reach. But that's what makes this question so electrifying. It's not just about bending time, it's about probing the very rules that hold reality together. And until we crack those rules, time travel remains the ultimate what if, dangling between the possible and the profoundly unknowable. Crush a star twice as massive as our sun into a sphere no wider than Manhattan, and you've got one of the universe's most extreme laboratories, a neutron star. Beneath its diamond-hard surface lies a realm where matter stops behaving normally, twisting into forms so bizarre they defy textbook physics. Imagine taking Mount Everest and squeezing it into a sugar cube. That's the level of density we're dealing with here. A single teaspoon of neutron star material would weigh 1 billion tons on Earth. But what's truly mind-blowing isn't just the crushing gravity, it's what happens to the particles trapped inside. At these unimaginable pressures, electrons and protons fuse into neutrons, packing together like cosmic sardines. Yet even neutrons have limits, go deeper, and quantum forces rip them apart, creating a soup of quarks, the fundamental building blocks of all matter. Swimming in a sea of gluons, the glue particles that normally hold quarks together. This quark-gluon plasma is thought to resemble the state of the universe millionths of a second after the Big Bang, a fleeting primordial broth we can't recreate in any lab on Earth. But neutron stars might be hiding something even stranger. Some theories suggest their cores could contain strange matter, a hypothetical form of material where up and down quarks transform into their exotic cousin, the strange quark. If true, this strange matter could be more stable than ordinary matter, turning anything it touches into a dense, quark-based crystal. A single grain could rewrite the laws of chemistry as we know them, though thankfully, no neutron star shrapnel is headed our way. The real challenge: we can't peek inside. Instead, astronomers rely on cosmic hiccups called pulsar glitches, sudden speed-ups in a neutron star's spin, to probe its secrets. These glitches might occur when the star's rigid crust cracks under strain, releasing pent-up energy from the superfluid core beneath. Picture a spinning ice skater pulling their arms in, but with enough force to shatter continents. Yet even these clues leave gaps. Some glitches are too large for current models to explain, hinting at phenomena we haven't even imagined yet, like quantum vortices tangling in the star's depths or phase transitions rearranging its core. That's the tantalizing dilemma with neutron stars. They're both astronomical objects and particle physics experiments, cosmic Rosetta Stones that could unlock how matter behaves under conditions we'll never replicate. Every flicker, every glitch, every pulse of radio waves is a message from a place where the rules bend and where the universe keeps its most guarded secrets. Imagine three siblings born from the same stellar nursery: Earth, Venus, and Mars, each starting with a similar mix of gases and water. Yet today, one is a lush blue oasis, another a scorching hellscape shrouded in sulfuric acid clouds, and the third a frozen desert with whispers of ancient oceans. How did these planetary atmospheres diverge so dramatically? The answer lies in a cosmic tug-of-war between geology, chemistry, and sheer dumb luck. Start with Venus, the solar system's cautionary tale. Early on, it likely had oceans like Earth's, but its closer orbit to the Sun triggered a runaway greenhouse effect. As sunlight heated the planet, water vapor, a potent greenhouse gas built up in the atmosphere, trapping more heat, which evaporated more water, creating a vicious cycle. Temperatures soared to 800 degrees Fahrenheit, hot enough to melt lead. Worse, without a magnetic field to shield it, Venus's atmosphere was bombarded by solar winds, stripping away lightweight hydrogen atoms and leaving behind a thick blanket of carbon dioxide. The result, a pressure cooker atmosphere 90 times denser than Earth's, where the sky itself rains sulfuric acid. Now look at Mars, the tragic underachiever. Evidence from rovers reveals riverbeds and lakebeds, proof it once had a cozy atmosphere and liquid water. But Mars's small size sealed its fate. Its core cooled faster than Earth's, shutting off the dynamo that generates a global magnetic field. Without this protective shield, solar radiation slowly shredded its atmosphere, molecule by molecule, turning the planet into a freeze-dried wasteland. Today, Mars's wispy atmosphere is just 1% as dense as Earth's, too thin to retain heat or support liquid water for long. Which brings us to Earth, the Goldilocks planet. Our atmosphere didn't just luck out, it fought for balance. Plate tectonics recycled carbon dioxide into the crust, preventing a Venus-style meltdown, while our robust magnetic field deflected solar winds. Even life joined the effort. Early cyanobacteria pumped oxygen into the air, transforming the atmosphere into the breathable mix we know today. It's a fragile equilibrium, though. Trace gases like methane and CO2 still trap heat, just enough to keep us temperate but with a razor-thin margin. The lesson written in these three worlds. Atmospheres aren't static costumes planets where they're living, changing systems shaped by distance, size, and even biology. A slight shift in any factor, and Earth could have ended up a furnace like Venus or a relic like Mars. That's what makes studying them so urgent. These aren't just alien weather reports, they're mirrors reflecting back our own planet's precarious, improbable miracle. Deep in the void of space, invisible bullets hurtle toward us, cosmic rays traveling at nearly the speed of light, packing energies that dwarf anything we can create in particle colliders. The most extreme of these, like the infamous "Oh my God" particle detected in 1991, carried the kinetic energy of a baseball pitch in a single subatomic speck. That's like a grain of sand hitting with the force of a freight train. The question isn't just what these particles are, it's how they get catapulted to such mind-bending speeds. The cosmic accelerators behind this are anything but gentle. Supernova, the explosions of dying stars, are one likely suspect. When a massive star collapses, it doesn't just fade quietly, it detonates with enough force to outshine entire galaxies for weeks. This explosion sends shockwaves rippling through space, creating turbulent magnetic fields that act like natural particle slingshots. Electrons, protons, and even atomic nuclei get caught in these chaotic currents, gaining energy with each loop until they're flung into the cosmos like cosmic pinballs. But here's the catch: while supernovae are powerful, they might not be enough to explain the very highest energy rays. That's where active galactic nuclei come in, the monstrous engines at the hearts of distant galaxies, powered by supermassive black holes billions of times heavier than our Sun. As matter spirals into these black holes, it doesn't just vanish quietly, it's torn apart in swirling disks of plasma so hot they glow across the universe. Some of this material gets funneled into jets shooting outward at nearly light speed, where magnetic fields whip particles to unfathomable energies. Picture a surfer riding a wave, except the wave is a tsunami of magnetized plasma, and the surfer is a proton moving fast enough to circle Earth 7 times in 1 second. Yet even these cosmic powerhouses struggle to explain the oh my god particle. Some theories suggest collisions between galaxy clusters. The largest structures in the universe might act as colossal particle smashers. Others speculate these ultra-high energy rays could come from defects in spacetime itself, left over from the Big Bang. Or perhaps we're missing something fundamental about how particles interact with magnetic fields across interstellar distances. The mystery isn't just academic. Cosmic rays constantly bombard Earth, subtly influencing cloud formation and even potentially impacting electronics. More importantly, they're messengers from the most violent corners of the universe, carrying clues about how matter behaves under conditions we can't replicate. Every time one of these high-energy particles streaks through a detector, it's like getting a letter from a cosmic war zone written in a language we're still learning to decode. And until we crack it, these invisible bullets will keep challenging our understanding of the universe's most extreme physics. Picture the universe billions of years from now, a frozen, lightless graveyard where even time itself seems to slow to a stop. This chilling vision, called heat death, is one possible fate awaiting our cosmos, driven by the relentless march of entropy. Here's how it unfolds. As the universe expands, galaxies drift ever farther apart, stars exhaust their fuel, and black holes slowly evaporate into faint puffs of radiation. Eventually, every proton decays, every black hole vanishes, and the temperature of empty space drops to absolute zero. The cosmos becomes a vast, uniform void where no energy can be extracted, no motion, no structure, just an endless sea of equilibrium. It's the ultimate expression of entropy's triumph, where even the memory of heat becomes impossible. But heat death isn't the only contender. What if dark energy, the force accelerating the universe's expansion, becomes stronger over time? Enter the Big Rip, a far more violent finale. In this scenario, dark energy's push grows so intense that it overwhelms gravity, electromagnetism, even the nuclear forces holding atoms together. First, galaxies are shredded apart. Then, stars and planets are torn from their orbits. In the final moments, atoms themselves are ripped asunder, nuclei split apart, and space-time fractures into fragments. The universe doesn't fade. It unravels in a catastrophic crescendo, leaving behind a chaotic soup of disconnected particles. Then there's the Big Crunch, a cosmic echo of the Big Bang. If dark energy weakens or reverses, gravity could eventually halt the universe's expansion, pulling everything back into a singularity. Galaxies would collide in a fiery embrace, temperatures skyrocket, and all matter collapses into an infinitely dense point, a mirror of how it all began. Some theories suggest this could trigger a new Big Bang, birthing another universe in an endless cycle of expansion and contraction. It's a poetic idea, death as rebirth, the cosmos breathing in and out like a vast celestial lung. But the most haunting twist lies in black holes. Thanks to Hawking radiation, these gravitational monsters aren't eternal. Over unimaginable timescales, they leak energy, shrinking until they vanish in a final, silent explosion. The last remnants of structure dissolve, leaving only drifting photons too weak to interact. This slow evaporation ties all three fates together, whether the universe ends in cold stillness, violent rupture, or cyclical rebirth. Black holes are the final keepers of its timeline. The real puzzle: we don't know which force will win. Dark energy's behavior, the shape of space-time, even the nature of quantum vacuum fluctuations, all of it tips the scales toward one destiny or another. And that's what makes this question so profound. The universe's fate isn't just about distant physics, it's about whether existence has an expiration date, or if somehow, against all odds, it finds a way to begin again. What if everything we see, stars, planets, even our own hands, is just a fraction of reality? The possibility that our universe has hidden dimensions might sound like science fiction, but it's a serious hypothesis backed by some of the most sophisticated theories in physics. String theory, for instance, proposes that the fundamental building blocks of reality aren't point-like particles but tiny, vibrating strings. And for the math to work, these strings need to dance not just in the 3 spatial dimensions we know, but in 11 dimensions total. So where are the extra 7? One explanation is compactification, the idea that these extra dimensions are curled up so tightly they're smaller than an atom. Picture a garden hose. From far away, it looks like a one-dimensional line, but up close, you see it has a circular dimension wrapped around it. The universe might be like that, with microscopic dimensions coiled into shapes called Calabi-Yau manifolds, intricate geometries so complex even supercomputers struggle to map them. These hidden folds could influence how particles interact, creating the forces we observe in our 3-dimensional world without us ever directly seeing the extra dimensions at play. Then there's the wilder notion of brain worlds. Imagine our entire universe is a 3-dimensional membrane floating in a higher dimensional space, like a slice of bread in a cosmic loaf. Other brains could exist just millimeters away from ours, separated by dimensions we can't access. Gravity, unlike other forces, might leak between brains, explaining why it's so weak compared to electromagnetism or the nuclear forces. Some theories even suggest the Big Bang could have been triggered when 2 brains collided, an event that would have released enough energy to birth an entire universe. The holographic principle takes this further, proposing that our 3-dimensional reality might be a projection of information stored on a 2-dimensional surface at the edge of the universe, like a cosmic version of a bank hologram on a credit card. If true, it would mean everything we experience is essentially a shadow play, with the real action happening in dimensions we can't perceive. So why can't we detect these extra dimensions? For one, our senses and instruments are wired for 3-dimensional experience. A fish might never grasp the concept of up beyond its pond. Similarly, we could be biologically blind to higher dimensions. Particle colliders like the Large Hadron Collider have hunted for clues, tiny energy signatures that might hint at extra dimensions, but so far, no luck. The energy needed to uncurl compactified dimensions or probe brain worlds might be far beyond our current technology. That's the tantalizing frustration of this mystery. Extra dimensions could neatly solve puzzles like dark energy or quantum gravity if they exist. Yet the very nature of these hidden realms makes them maddeningly difficult to test. Whether they are curled up too small, floating just out of reach, or woven into the fabric of reality in ways we can't yet imagine, one thing's clear. If other dimensions are real, the universe is far stranger and far grander than we've dared to dream. Turn a telescope to the moon and you'll notice something odd. One side is smooth and dark with vast lava plains, while the other is rugged, pockmarked with craters, and almost completely devoid of those familiar dark patches we call Maria. This stark divide isn't just random chance, it's the result of billions of years of cosmic violence, gravitational tug-of-wars, and a quirk of celestial mechanics called tidal locking. First, the basics. The moon's near side, the one that always faces Earth, is dominated by those dark, flat basins formed by ancient volcanic flows. But flip to the far side, and it's a battered wasteland of impact craters, some so deep they plunge for miles. Why such a dramatic split? One key factor is Earth itself. Billions of years ago, when the moon was still young and molten, our planet's gravity tugged harder on its near side, keeping that hemisphere slightly warmer and geologically active longer. Lava bubbling up from below filled in craters, smoothing the landscape like cosmic spackle. Meanwhile, the far side cooled faster, leaving its surface exposed like a punching bag for incoming asteroids. But that doesn't fully explain the far side's extreme cratering. Enter the moon's early chaos. Around 4 billion years ago, the inner solar system endured a bombardment called the Late Heavy Bombardment, a hailstorm of asteroids and comets that scarred every rocky world. Without the protective blanket of an atmosphere, the moon took the brunt of these strikes, and the far side, already cooler and more rigid, preserved those wounds like a cosmic fossil record. Then there's the lunar crust itself. Seismic data suggests the far side's crust is thicker, up to 12 miles denser in places, making it harder for magma to break through and resurface the terrain. Some theories propose this asymmetry dates back to the moon's violent birth, when a Mars-sized object slammed into Earth, ejecting debris that coalesced into our satellite. The impact might have thrown more material to one side, creating a lopsided crust from the very beginning. This duality isn't just academic trivia. The far side's shielded position makes it a perfect radio-quiet zone for telescopes, free from Earth's electronic chatter. China's Chang'e missions have already begun probing this untouched frontier, and future bases could unlock secrets about the early solar system. So while the moon's two-faced nature might seem like a cosmic accident, it's really a time capsule, one that holds clues to how Earth and its companion evolved together, scarred and smoothed in ways we're still learning to read. Imagine a cosmic beacon so bright it outshines 1,000 galaxies packed together, a single pinpoint of light visible from the edge of the observable universe. These are quasars, the most luminous objects in existence, and for decades after their discovery in the 1960s, their power source was one of astronomy's greatest enigmas. The answer, when it came, was as mind-bending as the quasars themselves, supermassive black holes, not as dark destroyers but as the ultimate cosmic engines. At the heart of every quasar lies a black hole with the mass of billions of suns, but it's not the hole itself that shines. The brilliance comes from its frenzied feeding frenzy, a swirling disk of superheated gas and dust called an accretion disk. Picture a whirlpool of matter spiraling inward at nearly light speed, compressed and heated to millions of degrees by friction and gravity until it glows with the energy of 1 trillion stars. This is matter pushed to its absolute limits, radiating across the electromagnetic spectrum from radio waves to X-rays. The sheer scale is staggering. A single quasar can emit more light than our entire Milky Way, all from a region no larger than our solar system. But quasars don't just glow, they scream into the void with jets of plasma. These are no ordinary streams of particles. Accelerated by the black hole's insane gravity and twisted magnetic fields, the jets shoot outward at nearly light speed, stretching for hundreds of thousands of light years. The physics here defies earthly intuition. Particles in these jets don't just move fast, they experience time dilation where their clocks tick slower relative to the outside universe. From our perspective, these jets seem to move faster than light, an illusion caused by their angle and relativistic speed, bending reality's rules in ways that still stump physicists. What's truly wild is how quasars tie into galactic evolution. These aren't freak anomalies, they're teenage galaxies going through a hyperactive phase. The same supermassive black holes that power quasars today sit quiet and dormant at the centers of most mature galaxies, including our own. The difference: fuel. In the early universe, galaxies were gas-rich, feeding their central black holes a gluttonous diet of material. As the gas ran out or was blown away by the quasar's own radiation, the lights dimmed, leaving behind the sleeping giants we see today. That's the paradox quasars reveal. Black holes aren't just cosmic vacuum cleaners. In their youth, they were radiant tyrants, shaping the galaxies around them with their outbursts. Their jets carved voids in intergalactic gas, regulating star formation, while their radiation ionized the infant universe, clearing the fog of the cosmic dark ages. We're seeing the aftermath of that fury, the quiet middle age of objects that once ruled the cosmos with light, and that's what makes them so fascinating. Quasars aren't just relics, they're the key to understanding how the universe grew up. Galaxies shouldn't exist, at least not the way we see them today. Take a spiral galaxy like our Milky Way, those elegant arms swirling gracefully around a bright core. According to the laws of gravity, those arms should have wound themselves up like a cosmic watch spring billions of years ago, leaving behind a featureless disk of stars. Yet here they are, still spinning with balletic precision after over 13 billion years. The invisible glue holding this celestial dance together. Dark matter, this cosmic puppeteer, doesn't just keep galaxies intact, it sculpted them in the first place. After the Big Bang, while ordinary matter was still too hot and energetic to clump together, dark matter unaffected by radiation began forming vast, web-like structures under its own gravity. Picture a sponge with threads of invisible mass stretching across the early universe. These filaments became the scaffolding upon which normal matter could later condense, pooling at their intersections like dew on a spiderweb. Without this hidden framework, gas clouds would never have gathered enough density to ignite the first stars, let alone assemble into galaxies. But dark matter's fingerprints show up in stranger ways. Computer simulations of galactic formation, running the physics of the early universe forward, keep hitting the same snag. They predict hundreds of small satellite galaxies orbiting larger ones like the Milky Way. Yet when we look, we find mere dozens. The missing satellite problem, the likely culprit, dark matter's properties. If it were warmer, moving faster in the early cosmos, it wouldn't clump as readily, leaving fewer dwarf galaxies in its wake. Alternatively, interactions between dark matter and ordinary matter might have suppressed small galaxy formation, though we still lack definitive proof. Then there's the enigma of galactic rotation curves. Stars at a galaxy's outer edges orbit far faster than visible matter alone can explain, as if gripped by an unseen hand. Dark matter's gravitational pull solves this neatly. Its vast, diffuse halo envelops each galaxy, extending far beyond the visible stars. Remove it, and spiral galaxies would fling themselves apart like unspooling yo-yos. Even more bizarre, the way galaxies align along dark matter's cosmic web, forming threads and walls millions of light years long, with voids between them so empty they'd fit hundreds of Milky Ways. Yet for all its influence, dark matter remains stubbornly aloof. It doesn't collide with itself like normal matter, which is why galaxies can pass through one another in clusters with minimal disruption, their dark halos slipping through like ghosts. This also means dark matter lacks the friction to collapse into disks, explaining why galaxies have fluffy, spherical halos instead of flat ones like their starry disks. Every clue points to a universe where the visible is just the frosting, a fleeting shimmer atop a hidden architecture we're only beginning to trace. And that's the ultimate irony. The very stuff that built the cosmos may forever refuse to step into the light. For 500 million years, life on Earth played a cautious game, simple organisms drifting through the oceans, barely changing. Then, in a geological blink around 540 million years ago, evolution erupted. The Cambrian explosion saw animal life diversify at breakneck speed, filling the seas with bizarre creatures sporting hard shells, complex eyes, and the first backbones. What flipped the switch? Some scientists wonder if the answer isn't just in Earth's chemistry, but written in the stars. One tantalizing idea points to cosmic radiation. Around the same time as the Cambrian boom, Earth's magnetic field may have weakened dramatically, allowing an unprecedented flood of high-energy particles from space to reach the surface. This radiation bath could have supercharged mutation rates, giving evolution a sudden jolt of raw material to work with. Picture a genetic lottery where cosmic rays kept rolling the dice at hyperspeed, creating radical new body plans almost overnight. Then there's the comet hypothesis. Frozen within these icy wanderers are prebiotic molecules, amino acids, sugars, even the building blocks of DNA. A cluster of impacts during the Cambrian might have delivered a concentrated dose of these organic ingredients to Earth's oceans, like a cosmic spice kickstarting evolution's recipe. Some researchers even speculate that viruses hitchhiking on comets could have infected early life, transferring foreign genes that triggered explosive adaptation. But the real wild card, oxygen. For most of Earth's early history, the atmosphere held barely a trace. Then, suddenly, levels spiked just before the Cambrian. One theory suggests a celestial assist. A nearby supernova shockwave could have compressed interstellar gas clouds, triggering the birth of massive new stars whose intense radiation split water vapor into oxygen. Or perhaps a collision with an icy body vaporized vast reservoirs of trapped oxygen in cometary ice. This wasn't just a biological revolution, it was an environmental perfect storm. Rising oxygen met stabilizing continents, while shifting ocean currents mixed nutrients into a global broth ripe for experimentation. Life didn't just adapt, it innovated, exploring body designs so radical, like the five-eyed Opabinia or the nightmarish Anomalocaris, that they seem alien even to us. The Cambrian explosion might not be a purely earthly story. It could be the universe's way of reminding us how fragile and explosive the spark of complexity really is. A few cosmic tweaks to radiation, chemistry, or even celestial traffic patterns, and life's playbook rewrites itself in ways we're only beginning to imagine. Pluto's heart isn't just a cute quirk. It's one of the solar system's most dynamic landscapes, a frozen wonderland that defies expectations. At the center of this striking feature lies Sputnik Planitia, a vast, bright basin filled with nitrogen ice that behaves less like a frozen slab and more like a slowly churning cosmic lava lamp. When NASA, a New Horizons spacecraft, zipped past in 2015, it revealed a surface so young and unblemished by craters that scientists were stunned. This isn't some ancient relic, it's a living, shifting terrain where ice dances to the rhythm of Pluto's faint sunlight. The secret to Sputnik Planitia's brilliance lies in its nitrogen glaciers, which flow and reshape themselves over time. Unlike water ice, nitrogen ice is soft and malleable at Pluto's frigid temperatures, barely above absolute zero. Picture pancake batter spreading across a griddle, except this batter is a slush of frozen nitrogen, carbon monoxide, and methane creeping across the basin at a glacial pace. But what really sets this region apart are the polygonal convection cells. New Horizons spotted massive, geometric patterns in the ice that form when heat from Pluto's interior causes the nitrogen to rise, cool, and sink in a continuous cycle. Each of these cells can stretch up to 20 miles across, cracking and renewing the surface so efficiently that it erases impact scars almost as fast as they form. Then there's the heart's alignment, a coincidence so perfect it hints at deeper mysteries. Sputnik Planitia sits almost exactly opposite Pluto's largest moon, Charon, locked in a gravitational tug-of-war. Some scientists think the basin might be an ancient impact crater so massive it altered Pluto's rotation. shifting the entire dwarf planet until this icy depression settled squarely in its tidal embrace with Charon. Others suggest the nitrogen ice itself piled up over eons, creating enough mass to reorient Pluto's spin. Either way, this delicate balance between ice dynamics and orbital mechanics makes the heart more than just a pretty feature. It's a window into how even small worlds can have complex, active geology. But the real kicker, Sputnik Planitia, might hide an underground ocean. The way Pluto's heart interacts with its moon suggests something dense and sloshing beneath the ice, a layer of liquid water kept from freezing by the warmth of radioactive elements in Pluto's core. If true, it would mean this distant, frozen heart could harbor the very ingredients for life, wrapped in a shell of convecting nitrogen. That's the magic of Pluto's bright heart. It's not just a geological oddity. It's a reminder that even in the solar system's darkest corners, there's enough heat, movement, and mystery to keep us guessing. Look up at the night sky, and you're not just seeing stars, you're peering into the universe's grandest architectural marvels. Stretching hundreds of millions of light-years across, vast filaments of galaxies weave through the cosmos like threads in a spider's web, separated by enormous voids so empty they could swallow thousands of Milky Ways whole. This cosmic web is the largest structure we've ever discovered, and its origins trace back to the universe's very first moments. The story begins with quantum fluctuations, tiny, random ripples in the fabric of space-time that emerge during inflation, the universe's explosive expansion in the first fraction of a second after the Big Bang. Imagine blowing up a balloon with microscopic bumps on its surface. As the balloon inflates, those tiny imperfections stretch into vast hills and valleys. Inflation did the same to those quantum ripples, magnifying them into the seeds of future galaxies and galaxy clusters. Gravity then took over, pulling matter into the denser regions while leaving the emptier spaces to grow even more barren over billions of years. But here's the puzzle. While inflation explains the web's blueprint, the sheer scale of these structures still baffles scientists. Take the Hercules Corona Borealis Great Wall, a filament so massive it spans 10 billion light-years, a structure that, according to standard cosmology, shouldn't exist. Or the Boötes Void, a spherical emptiness so vast it's been called the Great Nothing, spanning 330 million light-years with hardly any galaxies inside. These extremes push our models to the limit, raising questions about whether inflation's quantum seeds were truly uniform, or if some deeper, unknown physics guided their growth. Dark matter plays a starring role in this cosmic drama. Its invisible tendrils form the scaffolding for the web, attracting ordinary matter like a gravitational magnet. Without it, galaxies would be scattered randomly, not strung along these colossal threads. Yet even dark matter's influence doesn't fully account for the void's eerie emptiness. Some theories suggest dark energy, the mysterious force accelerating the universe's expansion, might be actively stretching these voids wider, like a cosmic zipper pulling apart the fabric of the cosmos. The real mystery isn't just how these structures formed, but what they reveal about the universe's fate. The web isn't static, it's still evolving, with galaxies flowing along filaments like water droplets sliding down a window pane. Some simulations suggest that in the far future, dark energy could tear the web apart, isolating galaxy clusters in islands of light adrift in an ever-darkening sea. Others hint that the web's structure might hold clues to even bigger phenomena, like defects in space-time left over from the Big Bang, or hidden connections between universes in a multiverse. Mapping this cosmic web is like reading the universe's diary, page by page. Each filament, each void, is a testament to forces we're only beginning to understand, an invitation to explore not just where we are in space, but how we fit into the universe's unfolding story. And with every new survey, every deeper glance into the abyss, we find not just answers, but grander questions waiting in the dark. Black holes aren't the eternal prisons they seem. thanks to a quantum quirk called Hawking radiation. They slowly leak energy, fading away over unimaginable timescales. Picture the vacuum of space not as true emptiness, but as a simmering sea of virtual particles. These fleeting duos of matter and antimatter constantly pop in and out of existence, borrowing energy from the universe before annihilating and repaying the debt. But near a black hole's event horizon, things get strange. If one particle falls in while its twin escapes, the debt goes unpaid, and the black hole loses a tiny bit of mass to balance the cosmic books. Over billions of years, this quantum bookkeeping adds up, causing even the mightiest black holes to evaporate like ice in sunlight. This revelation by Stephen Hawking in 1974 solved one paradox but birthed another, the information paradox. According to quantum mechanics, information about particles can't be destroyed. Yet if a black hole evaporates completely, what happens to all the data about the stars, planets, and gas it swallowed? One radical answer: firewalls. Imagine the event horizon not as an invisible threshold, but a blistering wall of high-energy particles that shreds anything crossing it, preserving information in the process. It's like a cosmic shredder turning falling matter into scrambled code. But critics argue this violates Einstein's principle that free-falling observers should notice nothing unusual at the horizon. Enter soft hair, a gentler solution inspired by the mathematics of black hole surfaces. Just as a fuzzy peach carries microscopic ridges, black holes might be fringed with low-energy quantum excitations, subtle imprints that record what fell in. These faint patterns, dubbed soft hair, could encode information like a celestial hard drive, preserving it even as the hole evaporates. String theory takes this further, suggesting black holes are holograms. They're three-dimensional contents projected from a two-dimensional surface where data is forever etched. The debate rages because it's not just about black holes, it's about the nature of reality itself. If information can vanish, our understanding of quantum mechanics crumbles. If it's preserved in some exotic form, the universe might be far more interconnected than we dreamed. With every theoretical skirmish, we're not just solving a puzzle, we're rewriting the rules of how existence stores its deepest secrets. Mercury shouldn't be this heavy. For a planet so close to the Sun, small, scorched, and seemingly unremarkable, it packs a staggering amount of mass into its compact frame. If you could crack it open like a cosmic egg, you'd find an enormous iron core making up nearly 85% of its radius, leaving just a thin shell of mantle and crust. Earth, by comparison, has a core that's only half its diameter. So how did Mercury become the solar system's overstuffed dumpling? The answer might lie in a cataclysmic collision so violent it reshaped the planet forever. Picture this: 4.5 billion years ago, the inner solar system was a demolition derby of protoplanets. Mercury, still in its infancy, might have been sideswiped by a rogue body up to a quarter of its own size, a glancing blow powerful enough to blast away much of its rocky mantle but leave its dense iron heart intact. Computer simulations show such an impact could have vaporized vast amounts of Mercury's outer layers, leaving behind a stripped-down, metal-rich wreck that eventually cooled into the oddball we see today. The missing mantle material, it could still be floating through the solar system as debris or even embedded in other planets, but not everyone's convinced by this cosmic hit and run. Some scientists argue the composition of Mercury's birth cloud might hold the key. The early solar nebula wasn't uniform temperature gradients, could have concentrated more metal-rich dust close to the Sun where Mercury formed. Imagine baking a layered cake where the bottom tier is extra dense. Mercury might have simply condensed from the heaviest available ingredients, no collision required. Supporters of this theory point to Mercury's unusually high sulfur content, which suggests it formed under reducing conditions where oxygen was scarce, a chemical fingerprint consistent with a metal-rich birth environment. The debate gets even stranger when you consider the Sun's role. young stars often go through a violent phase called the T-Tauri stage, blasting out extreme solar winds that could have sandblasted Mercury's outer layers over time. Think of it as planetary erosion on a grand scale, where the sun itself acted like a cosmic power washer, stripping away lighter elements while leaving the dense core exposed. Each of these theories impact nebula chemistry or solar ablation has its own flaws. The collision model struggles to explain why Mercury's remaining mantle hasn't mixed more thoroughly with the core. The nebula hypothesis has trouble accounting for the sheer scale of metal enrichment, and solar winds alone probably couldn't remove enough material to create such an extreme core-to-mantle ratio. That's why NASA's MESSENGER mission was such a game-changer. By mapping Mercury's surface composition, it detected unexpected amounts of volatile elements like potassium and sulfur, materials that should have boiled away if the planet had endured a high-energy impact or prolonged solar roasting. These findings muddy the waters, suggesting Mercury's history might be a hybrid of multiple processes: a metal-rich birth, a grazing impact, and relentless solar weathering all playing their parts. The deeper we dig into Mercury's secrets, the more it challenges our assumptions about planetary formation. Whether it's the scarred survivor of a primordial crash or a cosmic tax collector hoarding heavy elements, this tiny world reminds us that even the most familiar corners of our solar system still hold mysteries waiting to be unraveled. And with the Bepi Colombo mission now orbiting Mercury, we might finally get the clues we need to crack this dense enigma wide open. Deep in the ice of Antarctica, scientists are hunting cosmic ghosts, particles so elusive they pass through entire planets like they aren't even there. These are ultra-high-energy neutrinos, and they carry secrets from the most violent events in the universe. Unlike light, which can be bent or blocked, neutrinos travel straight from their sources, offering an unfiltered glimpse into cosmic chaos. But here's the puzzle. Some pack energies 1,000,000 times greater than anything our most powerful particle colliders can produce. Where do these interstellar speedsters come from? The answer might lie in two of space's most cataclysmic phenomena: blazars and tidal disruption events. Blazars are the particle accelerators of the cosmos, supermassive black holes at the centers of galaxies, firing jets of plasma directly at Earth. Imagine a lighthouse beam, except this one's made of matter moving near light speed, twisted by magnetic fields into a spiral of destruction. When particles in these jets collide, they can spawn neutrinos with enough energy to cross the universe unimpeded. In 2018, the IceCube Neutrino Observatory, a network of sensors buried a mile under the Antarctic ice, traced one such neutrino back to a blazar 4 billion light-years away. It was like finding a single bullet's origin in a cosmic war zone, confirming these monstrous black holes as neutrino factories. But blazars aren't the only suspects. When a star strays too close to a black hole, tidal forces stretch it into a spaghetti-like strand of plasma, a tidal disruption event. As this stellar debris crashes back onto itself, it creates shock waves that could accelerate particles to neutrino-producing energies. In 2021, IceCube detected another high-energy neutrino coinciding with one of these cosmic feedings, suggesting these violent feasts might also be neutrino birthplaces. The real genius of IceCube lies in its simplicity. Its sensors don't catch neutrinos directly. They wait for the flash of light produced when a neutrino rarely bumps into an atomic nucleus in the ice. It's like listening for a single note in a symphony of static, but when they find one, the payoff is immense. These neutrinos are cosmic fingerprints, pointing back to their sources with pristine clarity. Yet mysteries remain. Some ultra-high-energy neutrinos arrive without any obvious source, hinting at hidden astrophysical engines we've yet to discover. Others might originate from beyond our galaxy, their birthplaces lost in the vastness of intergalactic space. Each detection is a clue in a grand cosmic detective story, one that could rewrite our understanding of particle physics and the universe's most extreme environments. What makes this hunt so thrilling isn't just the science, it's the sheer audacity of chasing particles that barely interact with matter. Neutrinos remind us that the universe speaks in whispers, and sometimes the softest signals carry the loudest truths. And with every flash in the ice, we're one step closer to decoding the messages sent by the cosmos itself. At scales so small they defy imagination, space-time itself might not be the smooth fabric we picture instead. It could resemble a frothing, churning foam, constantly bubbling with quantum fluctuations. This mind-bending idea, called quantum foam, suggests that at the Planck length about a trillionth the size of a proton, the very structure of reality becomes fuzzy and uncertain. Particles wink in and out of existence, and space-time twists into fleeting, probabilistic knots. It's as if the universe's foundation is built on a seething ocean of microscopic turbulence, far too tiny for even our most powerful microscopes to detect. So how do we study something this elusive? One clue comes from the far reaches of the cosmos. Light traveling billions of light years from distant quasars, some of the brightest objects in the universe might carry subtle fingerprints of this quantum foam. Imagine a beam of light traversing the universe like a hiker crossing a mountain range. If space-time is smooth, the light arrives crisp and clear. But if space-time is foamy at the smallest scales, the light's path should jitter ever so slightly, as if the ground beneath the hiker's feet were constantly shifting. Some theorists argue that this jitter could subtly blur or delay high-energy gamma rays, creating tiny discrepancies in their arrival times. Yet the evidence remains tantalizingly ambiguous. Observations of gamma-ray bursts from distant galaxies sometimes show hints of these delays, but the effects are so minute they flirt with the limits of our instruments. Alternative explanations, like interactions with interstellar dust or magnetic fields, muddy the waters. Competing theories suggest that if quantum foam exists, its effects might only manifest at energies far beyond what we've probed, leaving this cosmic froth just out of reach. Even wilder is the possibility that quantum foam could challenge our notions of causality. If space-time is inherently fuzzy at microscopic scales, the very idea of before and after might break down, allowing particles to briefly tunnel through time or take multiple paths simultaneously. Some models propose that this foam could spawn microscopic wormholes or even entire baby universes, bubbling up and vanishing before they're ever detected. The real puzzle isn't just whether space-time foams. It's what that means for the nature of reality itself. If the vacuum of space isn't empty but alive with quantum turbulence, then the universe might not be a static stage but a dynamic, ever-changing entity, rewriting its own rules at scales we're only beginning to theorize. And that's the thrilling uncertainty at the heart of this mystery. The foam might be invisible, but the questions it raises are impossible to ignore. The sun's surface simmers at a toasty 5,500 degrees Celsius, hot enough to vaporize steel. But rise a few thousand kilometers into its wispy outer atmosphere, the corona, and temperatures soar to over 1,000,000 degrees. It's like stepping away from a campfire and suddenly feeling blistering heat instead of cooling air, a violation of common sense that's baffled scientists for decades. How can the sun's atmosphere be hundreds of times hotter than the surface below? The answer might lie in the invisible dance of magnetic fields and explosions smaller than a pixel on a solar telescope. Start with the sun's magnetic spaghetti. Our star isn't a solid ball but a swirling plasma where charged particles twist magnetic field lines into knots. These loops can snap like overstretched rubber bands in a process called magnetic reconnection, releasing energy in bursts powerful enough to heat the corona. Imagine two rubber bands crossed and tangled. When they suddenly recoil apart, the stored tension explodes into motion. On the sun, that energy doesn't just vanish, it's converted into heat, accelerating particles to insane speeds and superheating the surrounding plasma. Satellite observations like NASA's Solar Dynamics Observatory have caught these reconnection events in action. with loops of plasma collapsing and rebounding in slow-motion fireworks. But reconnection alone might not solve the puzzle. Enter nanoflares, tiny solar explosions theorized by physicist Eugene Parker in the 1980s. Each one packs just a billionth the energy of a typical solar flare, but they could occur millions of times per second across the sun's surface. Picture popping popcorn. A single kernel won't warm the room, but a constant barrage fills the air with heat. Recent data from the Interface Region Imaging Spectrograph mission supports this, revealing countless microjets and brightenings that could be nanoflares in action. If confirmed, it would mean the corona isn't steadily heated, but constantly sparking like a cosmic static shock. The truth might be even stranger. Some theories suggest plasma waves, ripples in the sun's magnetic field, could ferry energy upward like ocean waves carrying heat to shore. Others point to switchback magnetic fields, zigzagging structures spotted by the Parker Solar Probe, which might act like particle accelerators for the corona. Even the solar wind, that constant stream of charged particles, could siphon energy through turbulence, like whirlpools transferring heat in a boiling pot. What makes this mystery so compelling isn't just the science, it's the stakes. Understanding coronal heating could help predict solar storms capable of frying satellites and knocking out power grids. Every unanswered question about those million-degree flames reminds us how much we still don't grasp about the star that gives us life. And that's the irony. The closer we look at the sun, the more it reveals how little we truly see. Jupiter's Great Red Spot isn't just a storm, it's a solar system record holder, a swirling tempest that's raged for at least 400 years while Earth's mightiest hurricanes fizzle out after weeks. This crimson vortex, wide enough to swallow Earth whole, defies every expectation of how planetary weather should behave. The secret to its stubborn longevity lies in the radical differences between Jupiter and our own planet, a combination of sheer scale, bizarre atmospheric chemistry, and a lack of earthly inconveniences like land or oceans. Start with the fuel. Hurricanes on Earth draw energy from warm ocean water, which is why they weaken rapidly over land. But Jupiter has no surface, just an endless abyss of hydrogen and helium gas thickening into exotic metallic forms under crushing pressures. The Great Red Spot acts like a self-sustaining atmospheric engine, powered not by tropical heat but by Jupiter's own internal warmth left over from its formation. Heat wells up from the planet's depths, colliding with frigid upper atmospheric layers to create towering convection currents. These vertical wind shear patterns keep the storm spinning like a cosmic top, with no continents or shallow seas to disrupt its flow. The Juno spacecraft's recent flybys peeled back more layers of the mystery. Its microwave radiometer revealed the storm route's plunge at least 200 miles below Jupiter's cloud tops, far deeper than expected. Unlike Earth's shallow hurricanes, the Great Red Spot is a towering atmospheric skyscraper, its foundation anchored in Jupiter's churning interior. This depth may explain its stability. With so much rotational momentum stored in its column, stopping the storm would be like halting a freight train mid-derailment. Color is another clue. The spot's distinctive rust hue likely comes from chemical compounds like ammonium hydrosulfide or organic molecules called tholins, dredged up from Jupiter's depths by the storm's intense updrafts. When exposed to solar ultraviolet radiation, these substances undergo reactions that paint the vortex its signature red, a process that might actually be sustained by the storm's endless churning. It's not just a weather pattern, it's a planetary-scale chemistry set. Yet even monsters fade. Historical records show the Great Red Spot has shrunk by nearly 50% over the past century, with its shape shifting from an oval to a tighter circle. Some models suggest it could vanish entirely within our lifetimes, while others argue it might stabilize at a smaller size. Whether this is part of a natural cycle or a sign of deeper atmospheric changes remains unclear. What's certain is that Jupiter's most iconic feature isn't just a static painting on the planet's face, it's a dynamic, evolving beast, one that challenges our understanding of how weather works when freed from earthly constraints. And that's what makes it so mesmerizing. The Great Red Spot isn't merely a storm. It's a masterclass in planetary extremes, teaching us that the rules we take for granted on Earth are just a tiny subset of what the universe allows. If black holes are cosmic vacuum cleaners sucking in everything that crosses their path, could the universe have the opposite, a cosmic fire hose blasting matter and energy outward with no way to enter? That's the tantalizing idea behind white holes, hypothetical objects that look like black holes run in reverse. While no astronomer has ever spotted one, these phantoms emerge naturally from the math of general relativity. Flip the equations describing a black hole's relentless gravity, and you get a region of space-time that only expels matter, a one-way exit from the universe rather than a point of no return. The concept gets even wilder when you consider their possible origins. Some theorists suggest white holes could be the other end of an Einstein-Rosen bridge, better known as a wormhole. Imagine a black hole's singularity funneling matter through a space-time tunnel, only to spew it out somewhere else or someone else through a white hole. It's the ultimate cosmic shortcut, at least on paper, but here's the catch: wormholes are notoriously unstable. Even if they exist, they'd likely snap shut in an instant unless propped open by exotic matter with negative energy, something we've never observed. Then there's the Big Bang connection. Some cosmologists speculate that our universe's violent birth might have resembled a white hole event, a sudden, explosive eruption of energy and space-time from an infinitely dense point. Unlike a black hole's collapse, the Big Bang was an expansion, a burst of creation rather than destruction. Could the two phenomena be mirror images, linked by the same physics playing out in opposite directions? It's a radical idea, suggesting that white holes might not just be mathematical curiosities but hidden chapters in cosmic history. But why haven't we seen one? If white holes exist, they'd be spectacularly bright, pouring out radiation and matter like a celestial geyser. One explanation is that they're incredibly short-lived, collapsing under their own gravity moments after forming. Another possibility is that they're hiding in plain sight. Some interpretations of quantum gravity suggest that when a black hole dies by evaporating through Hawking radiation, it might momentarily rebound as a white hole, a fleeting flash in the cosmic dark too brief to detect. The real brilliance of white holes lies in how they challenge our assumptions. They force us to ask whether the universe's rules are symmetrical, if every destructive process has a creative counterpart. Even if they're never found, these hypothetical objects remind us that the cosmos is far stranger than the limits of our telescope, and that some of its greatest mysteries might be lurking in the equations we've yet to fully understand. When NASA Pioneer 10 and 11 spacecraft ventured beyond the asteroid belt in the 1980s, they carried humanity's hopes and an unsolved mystery. These deep space pioneers, now drifting toward the stars, began slowing down ever so slightly more than expected, as if an invisible hand was tugging them backward. This tiny but persistent deceleration, just a fraction of a nanometer per second, squared, became known as the Pioneer anomaly, and for decades it haunted physicists with the possibility that our understanding of gravity might be incomplete. At first glance, the culprit seemed obvious: heat. The probes were powered by radioactive plutonium, and the warmth radiating from their electronics and power systems could have given them a minuscule push in the opposite direction. Think of it like a car idling. Even when you're not pressing the gas, the engine's heat makes the hood vibrate ever so slightly. Engineers calculated that uneven thermal radiation from Pioneer's dish-shaped antenna might explain the anomaly. But when they crunched the numbers, the math never quite added up. The deceleration was too consistent, too uniform across both spacecraft, as if something deeper was at play. That's when the theories took a wild turn. Some physicists proposed modified Newtonian dynamics, or MND, a radical idea that gravity behaves differently at extremely low accelerations. In this scenario, the pioneers weren't slowing down because of some external force, but because the very rules of gravity change in the vast emptiness of deep space. It's as if the universe has a hidden speed bump we've never noticed before, one that only appears when you're far from the gravitational pull of planets and stars. Supporters pointed out that MND could also explain why galaxies rotate faster than predicted without invoking dark matter, tying two cosmic mysteries together with a single tweak to physics. Yet others suspected more mundane explanations. Could the probe's thruster fuel have leaked, creating an undetected drag? Or was there an error in how we tracked their motions using Doppler shifts in radio signals? The debate raged until 2012, when a team of researchers painstakingly reconstructed decades-old telemetry data and thermal models. Their conclusion: asymmetrical heat radiation did explain most, if not all, of the anomaly. The pioneer effect, it seemed, was a ghost in the machine after all. But here's the twist: even after accounting for heat, some residual discrepancy lingers, a whisper of uncertainty that keeps the door cracked open for more exotic possibilities. The pioneer's journey reminds us that sometimes the universe's quietest signals hold the loudest questions. Whether it was thermal drift, a flaw in our equations, or something far stranger, this anomaly taught us humility. Even our boldest ventures into the unknown can become cosmic riddles waiting decades for answers, or leaving us wondering if we've asked the right questions at all. So there you have it, 30 cosmic riddles that defy our best answers, from the ghostly tug of dark matter to the explosive enigma of fast radio bursts, from the universe's baffling birth to its uncertain fate. Each question isn't just a gap in our knowledge, it's a beacon drawing us deeper into the cosmos' grand puzzle. Think about that. Every time we solve one mystery, the universe unveils another, as if it's reminding us the more we learn, the vaster the unknown becomes. But here's the beautiful part: these aren't just problems for scientists in lab coats. They're invitations to wonder, to look up at the night sky and feel that ancient itch of curiosity. Maybe you've never puzzled over quantum foam or singularities, but I'll bet you've stared at the stars and wondered what's out there. That's the same spark that drives astronomers, physicists, and explorers. It's what sent Voyager beyond the solar system, what pushes telescopes to peer back in time, and what keeps us asking why when the answers slip through our fingers. The universe doesn't owe us clarity. It doesn't have to make sense, but the fact that we want it to, that we've built satellites and equations and dreams to chase these mysteries, that's what makes humanity so extraordinary. We're stardust trying to understand itself, so stay curious, keep questioning, and if you love diving into these cosmic conundrums as much as I do, hit that subscribe button, because the universe isn't done surprising us. Together, let's keep unraveling the next great mystery. The cosmos is waiting.